Welcome, guys. So in this video, let's talking about the connection with the back measure and the Riemann integral. So this is the summary of the one-rootings approach for the. So this is the summary of the quick introduction for the finish about the real analysis. So this is previous video about the back Martin and the fractals and the back dominant convergence. These are very important one. So today, let's doing something connecting the back and the Riemann. So this is also very important. Okay, so I would say this video is basically talking about a comparison with the Riemann and the back. Okay, so before I start, I need to prove a theorem, which is very important. Okay, so lemma. So this lemma is we will use it. So if f is measurable and non-negative, and also if let's say f d mu. So when I write the integral, I use d mu, but when I write volume, I will just using the u. Also, if f d mu is 0, then you can prove that the points, so basically which is f is 0 almost everywhere. Okay, so this means what? This means if you define x, which is f of x, which is a non-zero. If you define x, which f of x non-zero, this volume will be 0. Okay, so this is almost everywhere. So this means that the point which is non-zero is 0. Okay, so this is simply understandable because f is greater or equal to 0. So if a measure is 0, that means your idea is that your intuition is that the non-zero points, there is this set has no measure. Okay, so it's measure 0. Okay, but how to prove this? Oh, by the way, this is the exercise, the very people like to prove in the key. So basically some exercise in the textbook. Okay, but let me just quickly prove it. Okay, so yeah, let's write it so that I can write E equals to let's say A union B. Okay, so where I define A is a point which x non-zero. Okay, so so what? So I need to claim that A is I need to claim that the measure on A is 0, right? So but this is difficult. I don't know how to do, right? So the usual techniques that I define En to be to be a set point x such as f of x greater than 1 over n. Okay, for each positive integer. Okay, so obviously A is union of En and from 1 to infinity, and En is measurable, right? So but En may overlap, right? So which tell you that U of A is less or equal to summation of U En from 1 to infinity. Okay, so now I can bound this En, right? Because En is greater than 1 over n. Okay, so now f d mu on E is greater or equal to A f d mu. Because A is a subset of E, is f is non-negative, also greater than En f d mu. For like there's a case that En may be empty, right? But who cares? Okay, so it becomes this. And this guy is greater than equal, since f on En is 1 over n, right? So this is 1 over n mu of En. But this guy is 0, right? Which tells you that mu of En is 0 for every n. So which proves that the mu of A is less or equal to 0. So mu of A is 0. Okay, so this is a proof is theorem. And this is a very common techniques that usually you will use this. Okay, so have this theorem, we now can do the comparison. Okay, so now let's consider the Riemann integral. So consider AB open interval as a closed interval on the one dimension. And now I write, so remember, so that I write R, AB f of x dx to be a Riemann integral, So I think everybody remember what is the definition of Riemann integral. I will record. And I used original ABF dx as the back integral. Okay. And yeah, it's just the usual back integral on a real line. So now I have these two different concepts of integral. Okay, so theorem. The first theorem says that if f is a Riemann integral on AB, so let's write this. So f is a Riemann integral on AB, then f is the back integrable. So f is the back integrable, and what? The back integral will be the same as Riemann integral. Okay, so ABF dx will be R ABF dx. This is Riemann integral. This is the back integral. So if f is Riemann integral, then it's the back integral. Okay, so this is very deep theorem. B, let's say f is bounded on AB. Suppose f is bounded, then f is a Riemann integrable on AB. If and only if, right? This is a very famous theorem. F is a Riemann integral on AB if and only if what? The discontinuities has measure 0. Basically, f is continuous almost everywhere. Basically, what I'm saying is that the discontinuities, the discontinuity of f on AB has measure 0. Okay, so these are very, very famous statement. So f is a Riemann integral on AB if only if the discontinuity of f on AB has measure 0. It's just a simple story. When I was undergraduate, the first year that my professor told me this, I didn't understand what hell is going on. Okay, but now, I can prove this. Okay, proof. So let's prove AB and B. So let's notice this. So right, so my statement is what? F is a Riemann integrable, then F is the back integrable. So I can start from F is Riemann integrable, right? So let's define, let's say, right? So I can define, so PK is a refinement, and PK plus 1 is some, sorry, PK is a partition, PK plus 1 is a refinement. So what Riemann integral says that, what Riemann integral is that if you given a PK for F, and then you can compute the so-called lower sum, and you take each k to be infinity, basically you try to partition to very, very small. Then this is in Riemann notation, this is called the lower, basically this is lower sum, and then this is the lower integral. Okay, and then you can define the upper integral. Let's define to be f this. Okay, so R means Riemann. Okay, so from now I just using the partition and write down definition. So f is a Riemann integral if these two are the same. Okay, but let's pretend that these two can be different. Okay. Okay, so now this is partition, right? Let's say PK is x0, x1 up to xn, and then let's say s0 is a, xn is b. So in order to connect with the back, right, we need a simple function. Because remember that the back integral start from define a simple function on the back integral. So we need to connect. We need to use the simple function, right? So what is the common simple function that I can use? Just the minimum and maximum, right? So let's define a ukx, which is a function such that which is mi, and lkx, which is small mi, and let's say for x greater less than xi minus 1. So this is just let me just maybe draw something, right? So let's say this is my partition. I use this is AB. Okay, this is AB, and this is x1, x2. So this the minimum on each intervals. So this guy is L. and the maximum, which maybe from these directions, maybe this one, this one, this is the maximum, right? And for this part, for this one, where this is maximum, and for this one, this is maximum. Okay, so this one is a UK, right, for this partition. So this is LK so K is the labeled partition, right? So this is L2, maybe let's say 1, 2, 3, 4. Who cares, right? So the partition is not, the K is not important because just a refinement. So this is this L, this is U. Okay, so which is a simple function by definition. Okay, so obviously that I can define L PKF to be the integral of LK dx. So this is the back integral, and I can define the U PKF to be UK dx. Okay, and notice that when I do the partition, right? When I do the partition, the L will increase and the U will decrease, right? So which I have L1 greater or equal to L2, up to like f of x and greater or equal to less or equal to because you always choose a maximum, right? So it is U1 U something, right? But U2 U1. Okay, so notice these two are what? These two are monotone, right? So so now there's a trick, right? So you can I define, okay, so I can define L of x to be limit k goes to infinity LK of x, U of x, limit k goes to infinity UK of x. So these two are what? These two are monotone, right? So by analysis boundary above, so these two are always exist pointwise, and they are measurable because these LK are simple function, right? So L are measurable. Okay, so LK and what? And the UK are measurable. So their limits L and U are measurable. And we also have L less than F less than U, right? So we can do the back integral, right? Because they are measurable. And right, and they are bound, let's say, so L dx, let's say AB, which is the back integral. So okay, so up to now we haven't proved. Okay, so up to now we haven't proved F is integral. Okay, so let's do not do this. We only know L and U are integral. But since since L and U are what? Are simple, right? So we get the L dx equals to this. Okay, so now let me just write down what. Okay. Why? So notice that L, so L is L and U are integral. So this is the back measure. But we have what? We have monotone convergence, right? So by definition, when you approach k to be infinity, this gives you R lower f dx. In this case, this LPKF is LK dx, right? So these limits can pass into the can pass with the integral. So this is using the monotone convergence. Let me just write down. So using monotone convergence. L and U. Okay, so once you have monotone convergence, then you prove that the back integral, the back integral for L is the same as Riemann lower integral, and the back for upper function dx will be Riemann integral on upper dx. So what? So now we can use the final results. So suppose f is what? Suppose f is a Riemann integral, right? Which prove they are the same. So which prove that the L dx and the U dx are the same, right? Because by definition they are the same. But the problem is that L less or equal to U. So if you can write this U minus L dx, which is 0, right? And so this is non-negative. And then using our previous lemma, so our previous lemma, the non-zero parts. Okay, so let's see. So u minus L dx is 0. So what? So this means what? This means that L, this means L of x and u of x the same, right? Almost everywhere by our previous lemma. Okay, so if f and u are almost everywhere, means what? Means what? Means that if you see this, if you take limit, right, you will get what? You will get L. You will get what? You will get this, right? So if u of x, L x and u of x is almost everywhere on this f, which prove that what? F is the same as u and the same as L almost everywhere. So what? So it means that f is a Lebesgue integrable. Lebesgue integrable. Since u and L are Lebesgue integrable. So if these two are Lebesgue integrable and their difference is almost their difference is almost everywhere. Its difference is measure 0, then sure it will be measurable function. Lebesgue integral. Okay, so now we prove the first one. And obviously that if f is Lebesgue integrable, then your L will be f, right? Your simple function L will be lower and the upper will be LU will be upper, and they are the same. So easily show this. Okay. Now if it's bounded, then f is a Riemann integrable. I think this is trivial, right? Because we already and I should say so. Sorry, not trivial. So from here we need to prove this one. So f is a Riemann integrable on AB if only if the discontinuity of f on AB is has measure 0. Okay. Yeah, so B is almost trivial. Okay, so let's see. So notice that what? So if x let's say belongs to no pk, then and you can easily check that u of x equals L of x if and only if f is continuous on x. Okay, so this is your simple exercise, right? So if f is continuous at x, then you can easily say that u of x and L of x are the same. So, but we just proved what? We just proved that u equals f. U equals L almost everywhere. So which proves that f, the discontinuity of f, has measure 0. Okay, and surely if the discontinuity of f is measure 0, then L equals to u almost everywhere. Then you can use our previous construction. So prove f is a Riemann integrable by using a Lebesgue integral. Done. Okay, so that's it. Yeah, this is almost proof, right? Because f is measures. Yeah, okay. I think everybody knows the rest. Okay, so let me just maybe write it down. So basically, if f is so I think this direction is trivial, right? Because f equals to L almost everywhere, and we know this. Okay, so the discontinuity of f has measure 0. Conversely, if discontinuity of f has measure 0, then u will be equals to L almost everywhere. Then by our construction, f will equal to u and L almost everywhere, and both of these two are by definition are measurable. And so your f will be the Lebesgue measurable. Okay. But previously, this construction, if L and U are Lebesgue measurable, then by definition they will be equal to the Riemann lower integral and the Riemann upper integral. Now they are the same, so by definition they are Riemann integral if lower and upper are the same. Okay. Okay, and let me just write down some remark. So notice that if f is L on AB, so this is I just tell some story, and this can be proved in the future video. Okay, so you can define what you hope to define the. So from this notion, from previous notion, we know that the Riemann integrable should be the subset of the Lebesgue integrable, right? I mean on AB. So let's say you can consider f of x to be this. You can define this, right? Okay, so now notice that difference. So previously, if I talking about Riemann integrable, I can also define this. If f is a Riemann integrable, then I will have what? I will have the first fundamental theorem of the calculus. But now this integral is the back, so there should be something different. Okay. Then you can still prove something, right? You can still prove f prime equals f of x almost everywhere. Okay, so I will not give this proof, but basically this is just the modification. Okay, so conversely, let's say if f is a differentiable, suppose f is differentiable everywhere. Okay, so now it's very important that we need differentiable everywhere, right? So in the real analysis, there may be some function which which is differential is 0 almost everywhere. So basically, you can in the real analysis, you need f prime, you need this f differential everywhere, not just measure 0. This is not just almost everywhere, right? This is there's a so-called Cantor function which will violate this theorem, which is very, very tricky. Okay. And if let's say if f prime is the back integrable on AB, then you can show this. Okay, so this is the fundamental theorem of calculus by modified the back version. And I will not prove it. I will prove it in a future video, hopefully. Okay, and next time we will finish the introduction for the back theory. And I want to talk about L2 function and the complete metric space. See you guys.